Hello, my name is Roger Hallman. I am a computer scientist at the Naval Information Warfare Center Pacific, as well as a DoD Smart Scholar at Dartmouth College's Thayer School of Engineering. Today, I'm going to give a quick overview of the data deconflation problem, which kicks off a 3-year collaborative research effort on data deconflation problems. I will begin by presenting some motivation for our problem and giving some background information. The second part of the presentation will present our approach to solving the data deconflation problem with the use of reinforcement learning and generative adversarial networks, after which I am happy to take some questions. Consider the conflated image on this slide. Can you find all 4 constituent images? State-of-the-art image classifiers like AlexNet are unable to correctly identify anything in this image. However, the astute reader would notice that AlexNet did suggest that this image is a wreck, and it is plainly a mess. This image is a visual analog to the flood of data that is being produced as sensor networks become more and more ubiquitous around the world. We will inevitably be computing on data sets that include superpositions and oversaturation that must be dealt with before meaningful work can take place. Classical solutions to deconflation problems are known as source separation problems, where we seek to separate an unknown number of signals that may have been mixed in an unknown way. Perhaps the most famous example is the cocktail party effect, a human being's uncanny ability to focus on a single voice in a noisy environment. These source separation problems are traditionally vector representable and additive. Thus, there has been great success pursuing solutions using well-established linear algebra and statistical computation techniques. Biologically inspired neurological computing and deep learning solutions have also shown promise, but often rely on assumptions of a priori knowledge or context. Certain subtleties can also present difficulties. For instance, recent deep learning approaches to the cocktail party problem have shown greater success in separating speakers in mixed gender conversation than in same gender conversation. Process query systems, which are the current state of the art, are useful at source separation in computer network administration tasks. Inputs are taken from network nodes and hypothetical process models are developed to explain the observed events. As with classical source separation solutions in the previous slide, process query systems are reliant on a priori assumptions for successful operation. For instance, a heuristic approach to estimate the number of processes, and so on. We are pursuing our work because it is not at all clear that classical source separation solutions or process query systems can be extended to problems with non-additive superpositions or categorical valued data objects that are not sampled from a uniform spatial or temporal grid, nor with real valued data. To the best of our knowledge, there is no general solution to the deconflation problem. So we move on to some definitions. So simple data is data coming from a single data source. Complex or conflated data consists of interwoven simple data coming from multiple sources. Data can be conflated in space, time, or semantics. Data deconflation is the separation of complex data into its simple constituent data, or constituent simple data, rather. We are utilizing deep reinforcement learning and generative adversarial networks to develop what we believe will be a more general solution to the deconflation problem. Revisiting the conflated image from earlier, we might estimate classifications based on smaller samples and then use a generative model to complete a class hypothesis. We could then filter in and out the generated constituent object to isolate, confirm, or eliminate it, thus enabling us to focus on other objects. While this is speculation about how a human might solve this problem, it is a reasonable starting point. So, for instance, we might sample a little bit of the school bus in this image and work on generating a school bus that seems to match what we see in this image, then filter that out to try and focus on other things. For instance, the polar bear, or the panda bear, not the polar bear. Moving from the conceptual assistance provided by our conflated image to a complex data stream of observed events that one might see administering a sensor network, we hypothesize that observed events are the result of numerous simple data objects or processes, and our goal is to use deep reinforcement learning and generative adversarial networks to build models of simple data that could reasonably be responsible for the observed phenomenon. We model simple data and process as state machines, which are individually sampled and randomly interleaved to create labeled training data. We use delabeled training sets to train neural networks for deconflation. Similar to playing a game, the data sequence is the game state and the label is the player action. This project is just kicking off, so there is much to do. Our immediate goal is developing a solid formalization of the deconflation problem as a state machine representation that is suitable to both classical source separation problems as well as emerging scenarios as we have discussed here. I am happy to answer questions here or by email. Feel free to reach out. Finally, I would like to thank the Naval Information Warfare Center Pacific and the DoD Smart Scholarship for their support of this effort. Thank you for your attention.